All right, so I'm going to show you here how to find the missing side. We did a little bit of this last week, but I saw a lot of mistakes on these problems where you have to subtract. So if we took a problem like this triangle here, okay, so you'll notice here I'll do a rough drawing of it, okay, 2, 5, and m. Okay, we know our hypotenuse is this side, and we know that one of the side lengths is 2 and one of them is unknown. Remember, with the Pythagorean theorem, what you end up doing is you're thinking of it in terms of squares. So if we drew this square here, and it's a little bit off this page, this square here and this square here, the Pythagorean theorem says that if you take this square and you add this square to it, they're going to be equal to the square off of your hypotenuse, that square there, okay? So how do we do that? Well, we're going to go 2 squared, okay, because that gives us 4, which is that area, plus this square, so m squared, because we don't know what the actual number is equal to 5 squared, okay? Most of you are doing some of this in your head already, so let's simplify it. 2 squared is 4, m squared is going to stay the same, and 5 squared is 25, okay? So if we know that this square plus this square equals this square, then we can kind of do some backwards stuff here and say, oh, well, this square minus this square is going to equal this square here. So we see that in the math here when we subtract 4 from each side. So minus 4, okay, because this one is 25, this one is 4, so if we subtract them, we get m squared equals 21, okay? Next, what you do is, how do we get rid of a square? Well, we square root it. That's the opposite function. So we're going to go square root of that side, a little bit messy, and we get that m is equal to, let me see, square root of 21. So you can actually leave it like this, square root of 21, or you can put it in a calculator and get what your approximate is. And I'm just going to plug it into my calculator here. Square root of 21 is equal to 4.6, about, if I round it. So that's how a problem like that works. I also want to show you what happens with, let me erase this real quick. When you have square roots. So let's take this triangle here, okay? Similar idea, okay? We know the hypotenuse, it's a square root of 85. We put the square root of 68 here, and here it's p. And they leave it in square roots because then they don't have to round, so it's the exact representation. Because remember, if you pop that in your calculator, you're going to get a number that goes on forever. It's an irrational number. So they just leave it in square roots here. Sometimes it's confusing because people get confused on how to work with square roots. But remember, we're going to do this square here, okay, pretending like that's a square, plus this square, and that's going to be equal to this square over here. So if we write that out, it's going to be square root of 68 squared, okay, plus p squared equals square root of 85 squared, okay? Square root of 68 squared is just 68. They cancel out. Square root and squared cancel out. We talked about that earlier in the year. Plus p squared equals 85, okay? Solve for that, do minus 68, and we get that p squared is equal to 17, all right? At this point, I think you know the next step already. I'll do it in a different color just so you can see. We're going to square root each side. Square root, p is equal to the square root of 17, and again, you can leave it like this, okay? You can, let me erase that, that's messy. You can leave it as the square root of 17, or you can pop in your calculator and you get square root of 17 is approximately 4.1. 4.1. Okay, so that's how you find them. That's how you use the Pythagorean theorem to find a missing side.